Imagine this. You turn the page of your Cambridge IGCSE 0478 exam paper, you spot a basic binary conversion question, you write down the correct number, and you move on, feeling absolutely great about it. But then, the results come back. You've lost crucial marks. Marks that literally could have been the difference between grade boundaries. Why? Well, because being mathematically correct just isn't always enough to satisfy the mark scheme.
0. That's it. That is the exact number of marks awarded to a shockingly common mistake that we see students making on their exam papers year after year. It's kind of the ultimate exam trap. You do the mental math, you write down a completely factual statement, and you get absolutely 0 credit for it. No way, right?
Let's do a quick topper autopsy on this exact scenario. Take a look at this answer. The binary number 10011 is 19. Now, if you wrote this in your exam, you would be factually correct. The Denary equivalent of 10011 is in fact 19. But, and this is a massive but, if the command word in the question was calculate, this technically correct answer completely fails to score any points. We are definitely going to fix this, but to do that, we first need to understand exactly what the examiner is actually looking for.
Section 1. The core mechanism. Why computers think in ones and zeros. Let's just establish the fundamental theory real quick before we jump into fixing that flawed answer.
So here's your precise syllabus-safe definition. We operate in Denary, right? That's a base 10 number system, meaning we use 10 digits, 0 through 9, to count and calculate stuff. Computers, on the other hand, operate in binary, which is a base 2 system. They literally only use 2 digits, 0 and 1. Now, you might also see hexadecimal popping up in your syllabus, which is a base 16 system. But for this explainer, we're keeping our focus strictly locked on the base 2 environment.
Now, what's really fascinating here is how our everyday human experience contrasts with how a machine processes data. Think about it. When you count to 10, you run out of unique digits, right? So you naturally roll over to a new column, the tens column. Well, in base 2, you only have a 0 and a 1. So you run out of unique digits instantly. You have to roll over to a new column much faster. But why exactly is the computer restricted to just these 2 states in the first place?
It all comes down to the hardware. All processing takes place using physical components, things like registers and memory. And these components are made up of millions of microscopic transistors. A transistor can basically either hold an electric charge, which the computer reads as a 1, or hold no electric charge, which it obviously reads as a 0. Plus, the logic gates that actually make the decisions about processing this data, they only have 2 options too, on or off. This physical reality is exactly why every single piece of data, text, images, sound, the whole shebang, has to eventually be converted into binary.
Section 2. The framework reveal. Step-by-step conversion. Okay, let's pivot and dive right into the practical mechanism here.
The absolutely crucial step here is mastering the 8-bit place value grid. Starting from the right, the value is 1. And as we move to the left, each column's value just doubles, so it goes 2, 4, 8, 16, 32, 64, and finally 128. This whole thing represents 1 byte of data. Now let's take that exact exam question from earlier, the binary number 10011. If we align it all the way to the right side of this grid, you can clearly see the 1s land directly underneath the 16, the 2, and the 1 columns.
So, let's break down how this actually builds into an examiner-approved calculation. Step 1, you write out your place values from 128 down to 1. Step 2, align your binary digits starting from the right. Step 3, multiply the binary bit by the column value. If it's a 0, well, it's 0. If it's a 1, you take the column's value. And step 4, just sum those results up. So 16 plus 0 plus 0 plus 2 plus 1 equals 19. That right there is the exact working out you need to visualize.
Section 3. Escalating the stakes, negative numbers, and the open loop. In just a second, I'll show you the examiner clue that changes the answer entirely. But first, let's look at what happens when a number goes negative. Take a look at the furthest left column here. In certain scenarios, processors are actually set up to see this 8th column, the 128 column, not as a standard value, but as a sign bit. If the digit in this sign bit column is a 0, it means the binary number is positive. But if that digit is a 1, it indicates the number being represented is actually negative. It fundamentally changes how you read the whole byte. Keep this tucked away in the back of your mind as we head back to our original problem.
Section 4. The answer, upgrade. Think like an examiner.
All right, let's transition back to that flawed answer from the beginning. It is time to apply our framework and think exactly like a Cambridge examiner.
The absolute secret to getting high marks lies in the command words. If a question asks you to state the Denary equivalent of 10011, writing 19 is totally fine, because state just requires a concise fact. But if the command word is calculate or show, the examiner is specifically testing your methodology. They don't just want the final destination. They literally demand to see the journey. Writing just 19 for a calculate question, that is a 0-mark response, simply because there's 0 working out shown.
To transform your ordinary revision into top-band exam answers, you should really run your responses through this mark schema thinking framework. First, what's the concept? Here, it's binary conversion. Second, what is the data? It's the specific ones and zeros they gave you. Third, what's the scientific reasoning? That would be the base 2 multiplication. And finally, does it match the examiner wording? For a calculate command, that wording demands visible math on the page.
And this brilliantly illustrates the exact difference. On the one hand, we have our topper autopsy, a 0-mark guess that basically just says, it is 19. On the other hand, we have our full-mark response. Look at the difference. The student has literally drawn out the place value table, mapped the bits right underneath, written out 16 plus 2 plus 1, and then concluded with 19. By leaving this obvious paper trail of evidence, you're locking in every single available mark. You are proving to the examiner that you didn't just guess or memorize the number.
Section 5, the Interactive Exam Challenge. Test your framework. Okay, now it's your turn. Let's actively apply what we've just learned to a slightly harder syllabus concept.
In the 0478 syllabus, we learn all about how sound is stored. Recording software measures the amplitude of a sound wave at very specific moments in time. And each amplitude is a denoting number that absolutely has to be converted into binary to be stored. So if a sound is recorded at 44.1 kilohertz, that means the computer is taking 44,100 samples every single second. That's massive. And the number of bits used to record each one of those samples, that's known as the bit depth, or the sample resolution.
So here's where I want you to pause and predict. If the exam gives you a specific 8-bit binary sequence from one of those audio samples and says, calculate the Denary amplitude, how exactly are you structuring your working out on the page? Just mentally map it out for a second. Right, you draw your 8-bit place value grid, starting from 128 on the left down to 1 on the right. Then, you'd align the sample's bits, write out the addition of those active columns, and finally state the sum. It's like a giant puzzle, and that framework never fails.
Real quick, if you are finding this breakdown helpful, remember to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've got plenty more structured guides just like this one to help you out.
Okay, so we've proven that showing your working is pretty much the only way to satisfy a calculate command word, right? And we now have this perfect 4-step conversion framework. But here is a massive problem. Drawing out grids and writing multiple lines of addition, it takes time. When the clock is ticking down in a real exam and you still have dozens of marks left to earn, how do you actually deploy this flawless multi-step answer system without completely running out of time? Well, you'll find the exact timing strategies and high-speed answer templates you need in our next explainer on timed answer writing systems, so I will see you there.